These next two questions really level up what we're being asked to do in terms of finding these intervals of increasing and decreasing. So again, I strongly suggest you try them on your own before you watch me walk through them. So, example 4. First thing to note, they have already given us the first derivative and they have factored it. Thank you very, very much. And now we're asked to find intervals where our h is increasing or decreasing. So this is way back to week 1. We're just making our plus minus table. And we can see, looking at our factors here, we have some critical values of x is equal to 2 and x is equal to -1. There, steps 1, 2, and 3, I think, are already done for us here. I don't remember what the steps were. I don't care about steps, but let's go ahead. We'll put this down. We have a critical value at -1. We have another critical value at 2. Again, at this point, we can plug in numbers to guess and check, and not guess and check, but see what's happening in those intervals. We know that those are values where our function either crosses the x-axis and or touches the x-axis. Or we can use our information about our polynomials to do this a little bit more quickly. We can look at this. If we were to multiply everything out, the leading term of this would be an x cubed, right? We have an x to the first power, an x squared. Multiply that all together, we get x cubed. So we have an odd degree and a positive leading coefficient. So we know the end behavior of this particular function is such that it ends high and it starts low, right? End behavior doesn't match up because it's an odd degree. And then since it's overall got a positive leading coefficient, it's going to end how our linear example just did. And so we can use that information. So we are below the x-axis. At 1, we see that that's where we have a degree of 2. So we have an even multiplicity on that particular 0, which means that if I'm thinking about my graph, I'm coming up to that 0 at 1 and we're bouncing off the x-axis. So we are still negative here. Wah, wah. All right, and then we come along to 2, and 2 has an odd degree, right? It has a degree of 1, so we switch over and we become positive. We will cross over the x-axis and meet that end behavior on the other side. So when we're trying to find our intervals of increasing and decreasing, our interval of increasing, there is just one. It's that 2 to infinity. And our interval of decreasing, well, here's where it actually is very handy that we're including 0 and our intervals of decreasing and increasing, because if I don't, I would have to do something different. But it looks like I have negative infinity up until 2. Now, if you're somebody who doesn't believe, disagrees with the faction that says we include those those endpoints, you would be writing something like this, because you would need to do this, or from -1 up until 2. So I again I'm pushing you towards how Brian Passwater, the man who made these notes, does it, how a lot of my friends on Twitter do it. But again, depending on instructors, you might find people who prefer the bottom answer here. All right, so let's tackle example 5. We now have a k. Wah, wah, wah. We're not given k prime, and we want to figure out where it's increasing and decreasing, and they've given us a small range to look at, a closed interval. Not closed, because we actually don't get to 2 pi. But that makes sense because we're in trig land, and otherwise things get messy. So let's look at this. We know we got to find our first derivative. We have our scalar multiple 2, derivative of sine is cosine, and then we have the derivative of x, which is just 1. Now, of course, we need to find our critical values. That is when this is equal to 0 or is undefined. And just like with all of the polynomials you've been looking at, trig, especially not all trig, but sine and cosine, don't have any issues where they're undefined. Again, the domain of sine and cosine, negative infinity to infinity, all real numbers. So we can go ahead and get rid of that undefined situation. We're just going to go ahead and set this equal to 0 to find our critical values. So we'll say, okay, 2 cosine of x minus 1 is equal to 0. And they've set us up with a pretty straightforward trig equation. We can go ahead and isolate that 2 cosine of x by adding 1 to both sides. And then we can go ahead and divide by 2 to further isolate. And then, of course, as things work out in trig land, so often we are now with something that falls on our unit circle, right? When is cosine equal to 1/2? Cosine starts at 1, it gets smaller, so it's got to be my pi over, pi divided by 6. Oh my God, pi over 3. I was like, what is 60 degrees? It's not 30, it's 60, pi over 3. So x is equal to pi over 3. And also, we've got to think about when it is going to be 1/2 again, which will happen in quadrant 4, right? I'm always thinking in two ways when I'm thinking about cosine. I am thinking about the graph because me and the unit circle are not good friends. And then I'm also thinking about the unit circle a little bit, mostly for like which quadrants are positive. But we just figured out this starts at 1, so then it goes to root 3 over 2, root 2 over 2, 1/2. So that was my answer at 60 degrees. And I'm going to come back all the way in quadrant 4 back to that same 1/2. So if it was here, that looks like pi over 4. Let's make it better, pi over 3. Um, we had the same reference angle, so 2 pi minus pi over 3. I talk this slowly because I have to think about it a lot. So that is 6 pi divided by pi or minus pi over 3, which is 5 pi over 3. Really hope I'm right. I do like a lot of hand holding with trig. So there we go. Pi over 3, 5 pi over 3. All that gives us are our critical values. We feel like we should be done. So now we got to make our plus minus table. 0, we don't, pi over 2 pi is way over here. We've got our pi over 3. Don't even have to make these things spaced out properly, but I will. I'll make them somewhat okay. There we go. So we have to think about 2 cosine minus 1 and what that would look like. Now, since I've already sketched out cosine, I'm in a good shape here. I could do some transformations to really think about what 2 cosine x minus 1 looks like. But in theory, all that's going to be happening is a shift downward, right? And a amplitude, that stretch, right? So this is going to be pretty much exactly what's happening with our cosine graph. We don't have any flips, any reflections over the x-axis. So we might be able to just immediately think, seems like this will be positive, then we'll be negative for a while, and then we'll go positive again because we know what the graph of cosine looks like. It starts high, goes low, and then comes back. So that is sort of an idea. Of course, you can plug in numbers, right? Like that is completely allowed. You could sit there and be like, okay, well, I know pi is somewhere between pi over 3 and 5 pi over 3. Let me just plug that in. Well, 2 times cosine of pi, all right, minus 1. All right, so cosine of pi, what is that, -1? She says with no confidence at all, but yes, it is -1. So it's -2, -3. Oh, so that is negative, right? And then I could try cosine of 0. Well, cosine of 0 is 1. 2 times 1 is 2, minus 1 is +1. Oh, okay, cool. That is positive. So you can plug in values to check always, or use your knowledge of the graphs. So if you don't have a lot of knowledge of the graphs, it's completely okay. Plug in values. I've talked too long, but we need to finish this up with writing our intervals of increasing or decreasing. So we are increasing on 0 to pi over 3 and 5 pi over 3 to 2 pi. You'll note I'm going to use a open thing. I'm going to use a parenthesis on the 2 pi just because that was given to me in the original interval I was looking at. I'm using hard brackets because of the way that this particular set of notes defines intervals of increasing, decreasing. And then our decreasing, this is just that pi over 3 to 5 pi over 3 section. And I guess it's been a hot minute, but let's go ahead and look at this graph really quick. Might as well, right? Let's change this up because we have the original. 2 sine of x minus x. Let's look at her. Okay. So we only care about a certain little section. Let me change my axes. Let's go from 0 to 2 pi. And let's step by pi over 3 so we can really see what's going on. Okay. Get out of here. So we can look at this thing. So it looks like from 0 to pi over 3, that's that part of the graph where it's increasing, right? 0 to pi over 3. And then we're decreasing. In fact, let me make that go away. 0 to pi over 3 is the increasing section, and we're decreasing up until 5 pi over 3, and then it switches again. So I will even go ahead and screenshot this and throw it into these notes so we can kind of see it. Obviously, this is different than the graph that we were talking about here because we're looking at the derivative graph, but this is the original function which comes back to our intervals. 0 to pi over 3, increasing, decreasing, right, until that 5 pi over 3, and then my face gets in the way, but that's where it goes back to increasing. So there you go.